So here you have the disk, like so, and you have a groove over here, and you have a mass at this particular point. The whole thing is spun with an angular speed omega. Okay, the mass is m. What I would like to do is go into the non-inertial reference frame. I want to sit on that disk and do the physics. Clearly, the disk is accelerating, and therefore I'm going to feel a pseudo force. And what's the pseudo force that I'm going to feel? Well, the pseudo force is going to be acceleration in this direction. But notice that acceleration depends on the position of that particle. If the particle is right at the center, it's not going to experience any centripetal acceleration, and it's going to stay right at that point. However, if the particle is off center, it's going to experience some sort of a centripetal acceleration, and therefore it's going to experience a centrifugal force. From my non-inertial reference frame, is going to experience a centrifugal force this way. Okay, so the only force acting, in fact, is centrifugal force. There are no other forces acting on it. So let's say it's right now at some random distance x from the center. Then, if I were to draw my mass over here, the only force acting on that is the centrifugal force, which is this way. And that centrifugal force is going to be mass times the acceleration, the centripetal acceleration from an inertial reference frame, and that is x. What is that? Is r omega square. So x omega square. So you get x omega square. And so clearly this thing will accelerate, at least from our point of view. It'll accelerate linearly from our point of view. Non-inertial reference frame point of view. So that acceleration is just some acceleration a, and let's calculate that acceleration. That's easy. F equals ma. So m x omega squared must be equal to m times a. So the acceleration that it's going to experience is x omega squared. Now notice that in reality, if there was no groove like this, then along with the motion along the radius, it would also have a tangential motion, and that is due to what is called as the Coriolis forces, which is a little bit complicated. It's usually out of the syllabus, and that's why this problem has a groove. So to make sure there are no tangential motions, but in reality there would be a Coriolis force, and the Coriolis force is something like the whole world appears to spin in the opposite direction, right? And that's also going to have some effect on that particular mass when you look at it from the non-inertial reference frame. Okay? Anyways, no Coriolis forces here whatsoever. So this is the only acceleration we have. We need to calculate its velocity when it reaches at this point from r by 2. It's left from r by 2, okay? Anyways, right now it's at some random distance. So what we're going to do is, since the acceleration continuously keeps changing, we cannot use any of our equations of motion because they only work for uniformly accelerated motion. There's only one way to solve this. We need to integrate this. So let's build a differential equation. So the acceleration we know is, let me write that over here. Acceleration is x omega square, and acceleration is dv by dt. So that is x omega square. But I want an equation with v and x. I want to get rid of t. And there's always a very simple trick for this. You multiply by dx in the denominator, and you multiply it in the numerator. This is actually the chain rule of differentiation. You see, x and dx and dx can be cancelled out. You basically get dv by dt. However, I'm going to keep dv by dx as it is, and dx by dt is going to be the velocity, x omega square. And voila! See what we have done. We have gotten rid of the time. Okay, we're going to keep the dx term on this side. So let me do that over there. We get v dv equal to x omega square dx, and we are now ready to integrate this guy. So let's integrate this fellow. V dv, the integral of omega square x dx. We need to be careful about the limits. What are our limits? Well, what is the initial velocity? The mass is just kept over there, so the initial velocity is 0. What's the final velocity? Well, that's what we want to calculate. We'll just call that as v. Okay, what's the initial value of x? Well, it's given in the problem that the initial value of x is supposed to be r by 2. Here it is, right? R by 2. So we're going to start from r by 2. And we want to find out when it's about to fall. So x value will become r when it's about to fall. Can you see that? So you have to integrate this from r by 2 to r. It's a pretty straightforward integral. You get v squared by 2. That should be equal to omega squared into x squared divided by 2. And we put the limits here. So let me continue on this side. So we have v squared equal to omega squared into x squared, but we now put the limits. So you get r squared minus r squared by 4. Please don't do a rookie mistake of first taking the square root and then applying the limits. No algebraic operations like square roots or squares or stuff like that before you apply the limits. First you apply the limits, then you do all the stuff. Alright. Now that we applied the limits, now we are free to do all the algebra we need to do. So omega squared into, we get 3r squared divided by 4. And so v is the square root of this guy. So you get a root 3 divided by 2 times omega times r. Now, this would be the final answer, except for the fact, remember, we had done all of this from non-inertial reference frame. And whenever you calculate something from non-inertial reference frame, please come back to the inertial reference frame and ask yourself whether this is the final answer. Now, when I come back to the inertial reference frame, let's see what we find out. Well, even in the inertial reference frame, we know that there's a speed in this direction. That velocity is going to be the same whether you look at it from the non-inertial reference frame or you look at it from the inertial reference frame. That's not going to matter because that's the radial speed, right? When you went into a non-inertial reference frame, you got a velocity perpendicular. This might sound a little complicated. Listen to me very carefully. Look, when you look at from the inertial reference frame, the speed appears to be this direction, radial speed. When you go into the non-inertial reference frame, it again appears to be radial speed. Now the radial speed is not affected whether you look at from the inertial point or the non-inertial point, because remember, you are rotating along with the disk, and when you rotate, you have this tangential velocity which gets neglected. And remember, tangential component and the radial component are perpendicular to each other, so the two vectors don't affect each other. So in simple terms, whenever you are in a rotating reference frame, the radial speed will be the same whether you look at it from non-inertial or inertial reference frame. So we have the radial speed, and this radial speed is going to remain the same in the inertial reference frame. So this is only the radial speed. But the fact to remember is, this particle now has one more speed, which is tangential. And we have to add up both the speeds together. So we already found what the radial speed is. Now we have to find what the tangential speed is. And the tangential speed at this point, well, that's pretty easy. The tangential speed, the moment he's about to fall out. So that's like, until it's connected over here. So it really depends on what the groove is, okay? So when it's about to fall out, it might get that, at that point, that tangential speed, it's about to fall. Before that, it has absolutely no tangential speed because of the groove. Okay, anyways, and that tangential speed is very easy, right? That tangential speed is just going to be equal to, let me just write that down. Vt is just r omega. That's the tangential speed. So the net speed is going to be the square root of Vr squared plus Vt squared. And that will be, you take r omega common out, and we will end up with a square root of 3 by 4 plus 1. So eventually we get the answer as r omega root 7 divided by 2. And that's the net speed with which the object falls off. Actually, the tangential speed is quite debatable, because you can say, well, it's not going to end up with any tangential speed because it's not allowed to. But you can also debate saying that, when it's just about to fall out, it gets that right tangential speed because the groove ends. Whatever it is, the main part was to calculate this point, this particular speed, alright? Okay, so I hope you're able to understand this particular problem.